Tienes que poner un poco más allá, si no nos ve la cámara.
Vale. So again, welcome to the Friday seminar. Today we have with us Susana Pedrosa, who is starting something completely different to astronomy, because she began in Bariloche doing things related to in Tucumán, doing something related to superconductivity. Then, then in Bariloche, she did a PhD with things related to colloids, and then she went back to Tucumán to do stars and stellar evolution, and then she met Patricia Tisera and started working on numerical cosmological simulations in Buenos Aires. She's a researcher from CONICET, and she's been doing stays in Durham, Paris, and Madrid. She was a professor in the Universidad Autónoma de Madrid for 2 years, and now she's back visiting for a few months. And she's going to talk about that component decomposition in cosmological simulations.
Okay, thanks. I have a very strong conviction about my research subject, as you can see.
Susana,
but no, yeah.
Sorry, if you're not on the stage, then the camera is not fighting at all.
Yeah.
No. Perfect.
Okay, and here is okay?
Yes, perfect.
Okay. Well, first of all, thank you for inviting me. Thank you for letting me talk about my recent work. I will speak a little bit about what we have been doing with my collaborations here in Spain with Sara and Rosa Domínguez Terreiro, and also I would like to tell you about the work of my research group back in Buenos Aires. That is, they are doing interesting things related with the morphological analysis of galaxies. So I decided to the main subject is morphological analysis, let's say. And well, let's go to the subject. So, first of all, well, why morphology, right? I decided to study morphology because morphology encode a lot of information about how galaxies assembly, how galaxies, the assembly processes of galaxies, how they interact, and how they are affected by different processes through the evolution, and especially how they are affected by the feedback because of the star formation that is known to be a problem in simulations, how to regulate how to regulate the star formation through the redshift in order to get in order not to overproduce a star at redshift 0. That's a big issue. One of my main interests is the point of view to study morphology of the galaxies is through the angular momentum context. Just to put in context what I'm going to talk about. Well, you know the very well-known relation between angular momentum and mass, the JM relation found by Fall, and then also by revisited by Romanowski and Fall, that describe the angular momentum budget in the different components of the galaxies, essentially at that time between just the disk dominated galaxy and the spheroidal ones. And later, this work was revisited by simulation and many simulations, and around 2015, many groups, Genel with TNG, Obreja with Nihao, Teklu with Magneticum, Zavala with Eagle, Patricia Tisera and me with an old simulation that we used to have called Phoenix Project. We all studied this relation, and on the one hand, all the simulation verified the proposal, the relation, the observational relation found by Fall. But this also allowed to dig into different properties of the galaxies through analyzing the angular momentum content. We did that at that time, and later we were analyzing with Maria Sol Rosito, that was a PhD student from mine. We were analyzing spheroidal elliptical galaxies, and then we find some interesting feature in the very inner region when analyzing the bulges of elliptical galaxies, and we always find inner disk or something that resemble inner disk, so that catch our attention, and we decided, or I decided to look a bit more about that, and it resulted that, in fact, the bulge is a very rich component with a very rich substructure, and in particular with a rotating component that imprint on the bulge several interesting properties, from shapes to angular momentum content, and all that comes with that. And this can be analyzed also in relation with bars, and well, that's what we are doing right now. We want to know how this inner component is formed. It's like a monolithical collapse at very high redshift. It's secular, and the relation between, there's a recent paper by Breda, an observational one, that I will describe later a little bit more, but it show or postulate that the exponential profile of the disk that is ubiquitous in all the observational studies doesn't reach to the very inner, to the very center of the galaxy, and falls outside the center. So this is very important in order to well decompose the galaxies from the observational point of view. So we also check the density profiles. I will show a little bit about that. And what is important to remark is that with Gaia, for example, we are going to get much more data about much more detail about the base center of the galaxy. In fact, Breda is, I think, right now asking for time for timing with Gaia in order to try to verify the proposal in this paper, but with direct observation through IFS, integrated field spectroscopy. So I think that in the near future we will have a very detailed observation of the bulge and the inner structure, and it's interesting to have it studied with simulation that allows us to see a lot of detail that in other way we won't have. So the other thing I want to just speak a little bit before showing the result is the composition problem, that is an actual discussion, because there are different methods for dissecting a galaxy. In a recent paper, Thog with Eagle, he compared, he analyzed different kinematical and dynamical estimator of that used in order to decompose the galaxy For example, the K-rod, the circularity, the spin, and essentially found that all the estimator correlate very well, and so they are all consistent in between them. And I'm talking about this because there are more sophisticated methods, but one have to wait what is better in each problem because of velocity and in the advent of huge amount of data that we'll talk about that also. And there's another way of decomposing the galaxies is using the non-parametric morphology. We did a work with Lucas Viñones, is a young researcher from my group in Buenos Aires, based in Gini and MABT coefficients. And it's, in this case, we work with images. Also, as you have already heard a lot about this, because this was the work of Sarah, another way of decomposing galaxies is using GCF, the galaxy structure finding from Obreja et al. And well, something that we have just finished is applying, or Sarah has just finished, is applying GCF to Eagle galaxies. And it's very interesting that the thing here that I think is the problem is the relation between tuning and automatic classification. How much do you need to tune a method when you go from one type of data, let's say zoom-in simulations or a small statistic, and then you want to apply to a big cosmological box like Eagle? And that's something you have to take in consideration when you choose the method to work with, to decompose the galaxy. And also the advent of the really big surveys like LLST, well, it is pushing absolutely all the last works in decomposition to the automatic classification using machine learning, because you can see that with the Sloan we have 10 to the 6 galaxy approximately, Euclid 10 to the 9, and LLST is supposed to have 10 to the 10 galaxies, so it is impossible to use the usual method to process such amount of data. So many new works are going to the automatic classification through machine learning. I will talk a little bit about that because that's the work of Viñones right now. So this I will not talk about because you already know Eagle. We work with two simulations. One is Eagle, the bigger box, the 100 megaparsec box. And with a new simulation, this I want to talk to you about. And this is a new project, a new simulation that we are working on. Is a collaboration between mainly Patricia Tiseri is leading the project in Chile. Well, Lucas Viñones, bueno, me. Nelson Padilla, Rosa Domínguez Tenreiro, y Roberto González. And this new simulation, always a completely random acronym, and this new simulation are zoom-in simulations, and we expect to have like a grid of, I expect 20 zoom-in simulations with different essentially with different environment. They are sought to be able to to allow to study the effect of the cosmic wave and the inflow and outflows of gas. So we are still building this simulation. We have run until now just 4 experiments. The code is the code we have been using with Patricia Tisera, that is based essentially on Pigatet, with a very well chemical model that have given us a very good result referring, for example, angular momentum content, metallicity, the size of the galaxies. And well, these are some details about the code. And the zoom-ins are selected from 2 boxes of 50 and 100 megaparsec. And there are 2 sets of initial conditions. The ones in charge of the initial condition are Luca Vignone and Roberto Gonzalez. And they work in 2 sets of different initial conditions. So we have 2 local, something like resemble local group galaxies, consistent with observations. These are the LG1 and LG2. These are the resolution. No, sorry, these are the halo masses. And also we have the P1 suite. The P1 suite is a suite of initial conditions made by Luca Vignone, and are 27 zoom-ins initial conditions. And in this case, we have 2 levels of resolutions, 10 to the 5, let's say the high resolution ones, and 10 to the 6 in dark matter, the intermediate resolution one. And all the simulations have the dark matter only counterpart. So this is just to show the one of the halos of CIELO. At different virial radius, 2, 5, and 10 virial radius, just to show you how they look. So the decomposition, what we are interested in analyzing just the inner part of the galaxy, this inner disk. So we use a rather simple method based on the circularity, let's say how ordered is the rotation. So we, with the threshold, we decide which galaxies are dominated by rotation and which one are dominated by dispersion. Dominated by dispersion. And then we use an energy criteria in order to distinguish which particles are bounded and unbounded. So the bulges are composed by bounded particles, but then we analyze inside the bulge, within these bounded particles, which one are rotating and which one are completely dominated by dispersion. So we have essentially 2 bulges, one dispersed bulge and one, let's say, inner disk or pseudo bulge, and there's many names to call it. Of course, the stellar halo that is formed by non-bounded particles. You can find another features like anti-rotative disk also in the very inner part of the exponential disk. And we studied some properties, or we are studying some properties from CIELO and from EAGLE. EAGLE has a statistic and CIELO allows us, CIELO has a great number of outputs. So the follow-up through time is can be very detailed. We have like 100 is the output in redshift. So that's an advantage of CIELO. In order to study, we can follow the progenitor of a particular object we are interested in with very detail. And well, with Eagle, we have mainly a statistic. Just to show a little about this decomposition, how it looks. These are galaxies, a couple of galaxies from CIELO. You can see here, this is the angular momentum in the set direction and energy. You can see here in different colors. The blue one is the exponential disk. The yellow is the halo, the stellar halo. And this gray one is the counter disk, let's say. And the red one is the bulge, the classical bulge, the dispersed bulge. And here you have something green, is the inner disk, or this pseudo bulge, the rotating bulge. This is for CIELO, and this is for Eagle, the same type of distribution. And you can see here in the histogram again the disk, the halo, the dispersed bulge, and the rotating bulge, and just how they look in a face-on image. So we are studying the densities. This mainly in relation with something with what I told you about the Breda results, and we want to be able to characterize the profile with a Sarsic index, because it's something that observers use a lot. But what we are dealing with is that the Sarsic index is very problematic when you try to fit. There is several details that could change completely the values of your Sarsic indices, the limits and something and things like that. But for example, something interesting is that we find this blue one is the exponential disk, and as Breda is expected to find and is postulating, the exponential disk falls as soon as it enters the inner region, the bulge region, let's say. So when observer, this confirms her hypothesis that is not correct to for the observer to subtract the complete exponential disk to the very inner center of the galaxy. The gray zone is the not well resolved zone. And you can see also in red the density of the dispersed bulge, and in green there, or here for CIELO, the profile of this inner disk. Here is we try the histogram of the Sarsic indexes we are obtaining. You can see that they are all around. This is a problem because they are all around 1 and 2. 1 is the index for a complete exponential profile, and this is a problem, an old problem with fitting the profile of the density of the galaxies, because we don't find an indexes of an Sarsic index of let's say 3 or 4, like you will expect from theoretical from a well-behaved bulge. Well, we are not sure if this is effectively, they are all almost exponential, or we have problem with the Sarsic index. That's something we are seeing right now. And then we decided to put in the JM relation that was so used a couple of years before. We decided to see where the inner disk fall. And you can see here, for example, this is the exponential disk. This is the inner disk, and this is the dispersed bulge. And this is for Eagle, this is for CIELO, right? And this is for Eagle. One interesting feature is that we find that both, well, the inner disk behave exactly like an exponential, the exponential disk, but with a lower content of angular momentum, as expected. But this change in slope for bigger masses that some authors, for example, Lagos in 2016, also with Eagle, they found not, they do not decompose, but they found this this change in slope, and well, they throw a lot of some hypotheses about why not this is not following the theoretical relation of n to the 2/3, right? But if you decompose and look for the different components, the rotating one and the dispersed one, you can see that the one that follow for bigger masses, most probably because of the merger history, that it began to be more important in here. That component follow, but not the supported by rotation. Also, we analyzed the stellar population ages and the formation time. We defined just to characterize the formation time of each component, we defined the T70. It is the time where the 70% of the mass has been assembled. And you can see here, red, always red is for the dispersed bulge, green is for the rotating bulge, and blue is the exponential disk. And you can see that in general, this is from Eagle. In general, both the rotating and dispersed bulge form at higher redshift. This is an example of one galaxy, but it's a very common feature. Both form at higher redshift, while the exponential disk is more secular and continue forming through all the evolution until redshift 0. And also, well, here is, if you can see, well, it's not, if you can see the points, here we are plotting with the median ages and see that for each one of the components, when the median age is that older, the amount of angular momentum seems to be greater. Here, just to show, because we think that this relation, and also as Fall has proposed in 2018, that there is something like the fundamental plane in elliptical galaxy. Well, we have a fundamental plane in general, that is the JM, and some this fraction or bulge fraction indicator plane, and the relation that is very useful at least to see qualitatively some tendencies. Here we have now instead of the median, we have plot the points just to put color with the different parameters. For example, the diffraction, the T2 total fraction, and as expected, for higher the diffraction, you have higher angular momentum contents. And here we have color with the with the CERCIC index, nothing clear yet, but mostly for the problem with the index. And here we have the T70, and there's a slight tendency for galaxies for older the older star have a more amount of angular momentum. And this I want to show, this is the last one, about the inner rotation. Here we are plotting the T70 of the inner disk versus the T70 of the dispersed bulge. You can see that, and it's colored by the this fraction of the total galaxy. You can see when you have a larger fraction of as more dominated by rotation is the complete galaxy, you have a younger internal disk, and you have a bigger, of course, a bigger mass fraction of internal disk when you have also a bigger disk fraction of the galaxy. So they are both related in some way. And just a comment about time evolution. This is something I'm doing right now with CIELO. As I say, we have a many step in time, so we can follow the evolution. What I did here is just to put the relation and see how it evolves through time. And it's interesting that the both rotating components don't evolve very much, but the dispersed one, the dispersed bulge is changing. Sorry, this is lower redshift to higher redshift, and there's a change in slope approximately from here. A change in slope that, for example, if you see Lagos 2016, they found a change in slope, but not analyzing all the discriminating component. They just put the complete angular momentum, and they found that the slope fall. But when you dissect the galaxy, you can see that fall comes from mainly the dispersed component. So that's about what I'm doing, and I want to talk about a little bit what I'm doing with the rest of my research team. Here's the work, the main work of Lucas Vignone. He's a young researcher, and right now he's working in unsupervised classification of galaxies using deep neural networks. And well, this is an schematic of how the deep neural network work. Let's say we have an encoder and a decoder, a latent space in here, and he's using images. He's using a sample of images from Eagle. He's using 42,000 images from Eagle that are masses greater than 10 to the 10, and in redshift through 0.1 until 3. So he has a big sample of galaxies, and he's using this sample of galaxies in order to try to classify these galaxies using this neuronal network. Well, the important thing about this is that once you train the autoencoder, this part of the network, let's say, he's using CNN autoencoder. When you train this part of the autoencoder, you can get very realistic images and a representation of that is very, very similar to the input galaxies. And what is important is that is unsupervised. So we do not have a sample of images to train to teach the the network, how to, this is this galaxy, this is no, we do not do that. Just enter the images and train the encoder, and we get a classification that I will show right now. And another important thing is that as galaxies have no canonical orientation in the sky, in the plane of sky, there's another thing you have to add is something called GAN networks that make these things invariant under rotation. So it doesn't confuse one galaxy with the same one when it's rotated. This is the important point. And all you have to do is introduce another, let's say, another filter in this zone in the latent space, and then you can have this equivariant under rotation method. So some of the results he's obtaining, you can see here. This is something important that I said is that the latent space is of so much lower dimension than is a space of lower dimension. So, for example, you can have this 2D representation of the result in the latent space called UMAP. So in this image, what we are seeing, each point is one image, one galaxy, and it can be seen that just with the train of the neural network, you can see that we have the left region of the plot is filled with the what is called the blue cloud, right? And this thin strip here in the right is the red sequence, and in between we have something like the green valley. This is a demarcation line to separate between them. As you can see, there's the network is very separate the galaxy without any training, any previous training is able to separate the galaxy just from the feature in the images. And in the right panel, there's a plot of the density, the KDE density of this same space. And as you can see, there's a lot of peaks, and this is indicating that besides the separation that you can see, for example, in the blue cloud and red sequence, there's more substructuring here because of all these peaking densities. We found 3 peaks for the blue cloud, 3 peaks for the red sequence, and 2 peaks for the green valley. And for example, another thing that the network detects is this here, and this corresponds to galaxies that have suffered a recent merger. And as you can see, just from the feature of the image, the network segregate that galaxies to here, to the lower right. And well, this is very important because with other methods, for example, with the method of I told you of Pignone 2019 with Gini M20, it wasn't easy to separate the galaxies that have been affected by mergers, and well, the network have done it very nicely. So this is a representation, a nice representation of what I'm talking about before. You can see here the three different substructures found in the blue cloud, the one found in the Green Valley, and the 3 found in the red sequence. And well, here are some examples of the galaxies in each region, and you can see that it's very consistent. You have here a very defined disk with arms, and then when you go to the red sequence, you have a typical spheroidal galaxies with no noticeable features, and well, the network is able to detect all the features that have the spirals. And well, you can use another morphological process in this latent space. For example, here's an example of the specific star formation rate that is completely consistent with the result I showed you before about the colors. And this is just because it's nice. Here you can see the same representation as before, but with an example of galaxy the galaxy that belong to each part. Here you can see the disturbed one by mergers, the ellipticals, and here more extended spirals. So we think that the method is performing nicely. And well, the nice thing is that again, Lucas Vignone has a couple of weeks before, he won a grant from Amazon. Amazon is trying to push people to use their clouds, and they have this Amazon cloud service. They have a lot of GPUs in the clouds, so this kind of thing is ideal to use in GPUs. And well, we propose a project for Amazon, a nice project. I think I have I have at last that not only uses astronomical images, but also in collaboration with the CONAE, the Spatial Agency from Argentina. We are using images from clouds, from satellites from clouds that some researchers studied to predict things about the climate change. And we can apply the same thing to astronomical images and to these images of clouds. So it's a nice project that we are just beginning. Another thing I wanted to say about the relation with morphology, this is Pedro Cataldi, a PhD student from Buenos Aires. He has been studying the relation of the shapes of dark matter halos and baryons. It's something that many works have investigated. And a nice result he found that I would like to show is that, well, it is well known that when you have baryons in dark matter halos, they become less triaxial and more spherical. This is a representation. Here we have a spherical. It is a representation for shapes, right? This is the axis of inertia, and you can. This is the sum for spherical, oblate, prolate, and triaxial. And of course, when you have baryons, when you have a bigger this to total mass fraction, you have more spherical. The halos become more spherical. But he looked for this just in the dark matter halos counterpart, and using the same bin, he found the same trend. So the thing is, yes, the halos become more spherical when less triaxial when baryons are present, but it seems at least that the disk prefer to form in already more spherical dark matter halos, and this is I think a nice result. And just this to finish, as I said before, one of the main things in order to get realistic morphology is to be able to better regulate the star formation. We have, as I also told before, an overproduction of stars at redshift 0. So we need new and more effective feedback processes. We are using the supernova feedback, for example, but right now we are trying to see the feedback from X-ray binaries at higher redshift, right? For this, this is led by Leonardo Pelliza, he's another researcher from my group. And we are using for that the first light simulation from Severino, from the one. And then these are zoom-in simulations that go from 5 to 15 in redshift, the 300 simulations. And what we are willing to see is, first, the characteristic, the main features of the galaxy at this redshift and cosmic dawn, let's say, and try to implement in galaxy of CIELO, in the CIELO code, this feedback. This is a result from a previous implementation by Celeste Artale in 2015 when she was making her PhD, but then this line was abandoned, and we are trying to go again with this and implement this feedback at high redshift that would be more effective in regulating the star formation and getting better star fraction at lower redshift. Just to take away the things, the main things I think is that morphological analysis is a very powerful tool to dig into the assembly process of galaxies. We have to be very aware of the advent of massive data acquisition that is changing the way we are studying the morphology. And of course, machine learning, deep learning, and all the automatized classification is becoming ubiquitous because it's needed for something like LSST. And that's all.
So if anyone has any question.
I have one.
Yeah.
I want to ask, this inner disk is, I do not understand, it's stellar or gaseous or both?
Oh, sorry. No. I'm studying just the stellar populations.
Yes,
I didn't look for that in gas still.
So there are circumnuclear gaseous disks observed in molecular gas. So these two are going to be correlated, or is some similar physics happening there, like in this inner region that, I don't know, about the specific angular momentum of both these objects?
Yeah, I want to say about that because, certainly we were talking about that, the Gadotti works with Muse. They found this nuclear disk observationally. And it would be nice to try to compare with that, yeah. And I think that I'm very confident that this inner disk is not innocuous and has to do with probably with the stability of the galaxy and features like that. So I think it is interesting to look about that. Yeah.
Okay. And I have another question regarding this region. In these results, do we expect the AGN feedback to have an impact on the content of specific angular momentum, especially in the bulge? Like,
yeah, I'm not quite sure because Well, we always say if we are still under 10 to the 12, we do not think about AGN, but I'm not quite sure. I really not quite sure if it will be affecting this. In general, when we have a Milky Way like galaxy, we do not take AGN feedback in consideration because it's supposed to be not very effective, but not quite sure if it can affect, yeah, the inner zone, especially, yeah.
So in the subgroup that you found with the autoencoder, right? So do they have like a physical interpretation, or is there a kind of more intuitive connection now between morphological types and certain physics that's going on with those galaxies?
Well, another properties besides the colors, let's say.
I mean, if I understood correctly, when you applied the autoencoder to these eagle galaxies, you found that there were like, I think, 7 or 8 subcategories, right?
Yeah.
And I was wondering whether there was a clear physics that explains why there were like 2 main groups and not 20, or not they were consistent within one group for the galaxy.
Yeah, the algorithm that clusterized the space is hierarchical. So I think it goes from the main features like just spiral ellipsoids, and then it began to look for a more detailed one. So you can see that the density peaks appears. And I guess there's more down there you can look, but it's like a hierarchical algorithm. Yeah.
But you couldn't link up to specific processes, the subgroups, or?
Yeah, it's something that Lucas has done is, as I said, we have a sample with redshift from 0.1 to 3. So you can follow 2 things. You can follow, for example, that is a plus. You can follow in redshift the galaxy from 1 to the progenitor. And one thing when you have this kind of sample, that is a plus to the classification, is that you expect the progenitor to have a similar morphology than the daughter or son, or the new galaxies. And also there is what they call semantic sense, that in the latent space you can follow some directions, and you can see this direction they call semantic direction. You can see that in this direction there's evolution of some properties. So you find a direction, and you can see that in this direction you can go from passive to active galaxy, for example. And yes, you found that kind of feature in the latent space. Yes.
Yeah, thanks.
Yeah. It's a nice method. Yeah.
So if no one else wants to ask anything, I think that was all. And thank you all for coming, and thank you, Susana, for the talk.